Alrighty, so let's take a look. This is page 6 and 7 in our motion packet. This one was by popular demand. Alright, so Chuck's riding the giant drop at Great America. If he free falls for 2.6 seconds, what's his final velocity going to be? The reason that we know that this acceleration is negative 9.8 is because we're assuming that this is on Earth, and Earth's gravity is always going to be a constant negative 9.8 meters per second squared of acceleration. Why negative? Because it's in the downwards direction. I think we talked about that in previous videos and in class, but if not, just realize that negative is because we're in the downwards direction. Okay, so how can we figure out what his final velocity is? Well, we're going to be using this formula, v minus v naught equals at. That's the only formula that deals with final velocity, right? So if we're dealing with a final velocity, we've got to use a formula that's got final velocity in it. We know our initial velocity is 0, because if he's on the giant drop, and I'm terrible at drawing to begin with, let alone on a tablet on the computer, but if this is our giant drop and all our people are sort of sitting around it, that's actually really good for me. I'm impressed. That's besides the point. But the giant drop's going to fall this way. The thing that is allowing it to fall is gravity, so that's what we already talked about. But our initial velocity is 0, because before it falls, it just sort of sits there until the person pushes the button or the ride does whatever it needs to do in order to get it to drop, and then it lets gravity do its thing. By the time it gets down here, its final velocity is at its maximum just before coming to a stop. So it tells us how long it takes to fall. If we know its acceleration and how long it takes to fall, we know its velocity. Be careful, it is a negative. Is that okay? Absolutely, right? Negative just means that we are going down. Doesn't necessarily mean, actually it doesn't mean that we're slowing down. It just means that we are falling down. All right, how far did Chuck fall? Well, if it says how far, we're looking for, normally we wouldn't call it a distance up, but distance, height is just simply a distance up. So that's why I can use this formula, this dy equals v naught yt plus 1/2 gt squared. Again, I know my initial velocity, that's 0. I don't even necessarily need to know my time, because this is going to be 0 anyway, no matter what my time is, but I know it. I put it in there just for the heck of it. And then 1/2 is always going to be part of the equation, right? Negative 9.8 comes again from my gravity, and then this 2.6, remember, it's got to be squared because that's part of our formula. After we go through and do the math, we come out with negative 33.124 meters. Well, did he fall negative 33.124 meters? No, the negative means that it's falling. So he fell 33.12 meters, and that's where I'm coming out with this from. The reason that it's not negative is because you don't fall negative. The negative just represents that's going down. So he went down 33.12 meters. All right, moving on to the next one. On the moon, a feather is dropped from a height of 1.4 meters. The acceleration of gravity on the moon is 1.67 meters squared. Meters per second squared. So I determine the time it takes for the feather to fall to the surface of the moon. Now, realize the feather would fall relatively quickly, especially in comparison to a person, because there's no air resistance on the moon. There's no atmosphere on the moon. Which is kind of interesting. That's besides the point. But if we want to figure out how long it took to fall, well, we know that it's falling a distance. So if I've got my moon made out of cheese or whatever the heck it's made, it looks like more like a bowling ball, whatever. But if I've got my feather, I don't even know what I'm trying to draw. There we go. It's a feather. And that's a terrible feather, even for me. I'm embarrassed. But that feather falls down to the surface of the moon. The thing that's pulling it down is gravity. Gravity in this case, because it's the moon and not Earth, is negative 1.67, because we know that the acceleration of gravity on the moon is 1.67 meters per second squared. But because it's gravity, it's negative, because it's pulling us down. Alright, determine the time it takes. Well, it's exactly like the previous problem now, just using a different value. So we know the initial velocity is 0 because somebody's probably holding it before they drop it. So it's just sort of resting there. End up going through doing our math, coming out with t squared equals 1.68. Take the square root of that because we don't care about t squared, we care about t. So I come out with 1.29 seconds. And remember, I can always take this 1.29 seconds and plug it back in here and make sure that both sides are equal to one another. So it would be like the left side is 1.4, so the right side, after it's plugged in and I do all my math, should be really close to 1.4. It may not be dead on because I'm doing a lot of rounding, but it should be really close. All right, take a look at number 3. The observation deck of a skyscraper is 420 meters above the street. Determine the time required for a penny to free fall from the deck to the street below. And it's actually a myth, by the way, that a penny, the students ask this every year. Is it true that if a penny fell from the top of the Sears Tower it would kill somebody? No, because it hits terminal velocity, and the way it's spinning, it wouldn't actually harm you. It probably hurt if it hit you in the head, but it's not actually going to harm you at all. And its mass is tiny as well, so you're all good. Go ahead and walk under Willis Tower. All right. So we know that if we're looking for the time required for a penny to free fall, we're going to be using this d equals v naught t plus 1/2 gt squared or at squared, however you want to label that, because remember the g is either from gravity, gravitational acceleration, or a is acceleration, which is coming from gravity either way, so it doesn't matter what you choose to do over there. But we know that the time required is going to be dependent on the pull of gravity. Well, this formula has the pull of gravity in it. The other formula that has gravity in it is this, but I don't know my velocity, so I can't really use this one. I know my initial, and I'm not going to be able to find my final because I'm not going to have my time, so that one's out of the question. So we can only be left with this one. So go ahead and plug everything in. Even though I'm solving for time and I don't know it here, it's going to be 0 times time. 0 times anything, including 0 times a variable, is 0. 1/2 of negative 9.8 is negative 4.9. You probably have that memorized by now after you've done a whole bunch of these problems. So then from there, isolate t squared, divide both sides by negative 4.9. Come out with t squared equals negative 85.7. Take the square root of both sides, and then you end up with t equals 9.26. Again, we take the square root because we don't care about t squared, we care about t. Get rid of squared by taking the square root. All right, stone. Next one. Stone's dropped into a deep well, and it's heard to hit the water 3.41 seconds after being dropped. Determine the depth of the well. That's kind of cool. Like, even if you're somebody that's not interested in physics, isn't it cool that the natural laws of the world, they're so consistent that we can actually figure out how deep something is just by simply dropping something and timing it. We don't actually have to measure it. Kind of cool. Dorky or not, it's cool. So 3.41 seconds it falls for. So keeps falling, and then we hear the little plop, and we time it 3.41 seconds. So again, the thing that actually gives me my time is gravity pulling me down, right, or pulling the rock down. So it's got to be a formula that has gravity in it, kind of like the previous problem here. We do have another formula with gravity in it, the whole v minus v naught equals at thing, but I don't have my final velocity. If I don't have my time, I can't solve for it I can't solve for final velocity in order to solve for time. It's just sort of this never-ending loop of, oops, I don't have that variable, I don't have that one, I don't have that one, so we can't use it. This is the only other formula that has gravity in it that we know, and since gravity is the thing that's pulling me down, I'm going to use it. Alright, so to begin with, my initial velocity is 0. I know that because it would be like the person's holding the rock in their hand, and before they drop it, they're holding it there, so it's just 0. It's at rest. They end up dropping it. It falls for 3.41 seconds at negative 9.8 meters per second squared. Go ahead, do your math from there, and you would find out that it is negative 56.98. Well, again, it's kind of like a couple problems ago where it's not that it's negative 56.98 meters. high, it's that it fell. That's what the negative represents, 56.9 meters. So if it fell that far, well, then that means that it's 56.98 meters deep, just not in the negative. All right, next one. Kangaroos capable of jumping to a height of 2.62 meters. Determine the takeoff speed of the kangaroo. So this one's a little more challenging because we've got to realize what's going on. If you diagram it out, you'll be in pretty good shape. So I would actually recommend starting here. All right, so it's takeoff speed. We need to figure out, but we know that it's going to have some sort of takeoff speed pushing it up. At some point it has to come to rest. So this point right here is going to be 0 meters per second. Now obviously it doesn't come to rest for very long. It'd be weird and just be kind of floating there in the air, and we know that generally doesn't happen. Actually, it never happens, especially with kangaroos. They don't like floating in the air. I don't know, I said that, it's weird. But if we end up going from a positive to a negative, well, in order to go from a positive to a negative, we have to pass 0. So that means at the maximum height, we are at 0 meters per second, no matter what. No matter how tall that distance is. It could be 1,000 meters in the air. It could be 1 centimeter in the air. The maximum is always going to be 0 meters per second. All right. So from there, I also know my distance, right? My height. We normally call this height, but really what that is a distance in the y direction. Well, the only formula that I have for distance in the y direction is d, I forgot the y here, dy equals v naught yt plus 1/2 gt squared or at squared, however you prefer it. So I know my distance in the y direction. This 0, this is interesting, right? Because this velocity up here, it's not really my initial velocity, but I can think of it as the velocity that I initially know. It's the first velocity that I know, so I'm going to use it. All right, so that's why I'm plugging in 0 over here. I don't know the time, but it's going to be 0 times time anyway. So plus 1/2 a or g, right, negative 9.8 t squared. So I'm going to go through, do my math, divide both sides by negative 4.9. I come out with 0.53, take the square root, we get 0.73. That's weird, right? Why is it that the time gets bigger? Well, it's because we're taking the square root of a decimal, something decimal smaller than 1. Well, if I'm dividing by something smaller than 1, I'm always going to get bigger. So in this case, it's no different. So that may seem like it's kind of odd, but it is in fact the case, again, because we're dividing by a number smaller than 0. Okay, so let's take a look at the second part then, because now I know that I am in the air for 0.73 seconds, or I'm taking 0.73 seconds to get up. I'm also taking 0.73 seconds to fall down. The reason that I know that it's 0.73 seconds to fall down is because of this 0. That 0 corresponds with my velocity at the very top. Well, at the top, that's only half the amount of time that I'm in the air for, right? Because it took me half the amount of time to get up, half the amount of time to get down. All right, so now I can figure out what my final speed is, because I know gravity's pulling me down at negative 9.8. I know my time that I was in the air for, at least the time that it took me to fall. I know my velocity at this point, even though it's not my true initial, it's the one that I do know. So if this is at 0 meters per second and I'm falling, well, then I'm at 7.154 meters per second at this point. That's my final speed, right? It's negative 7.154 meters per second. Well, if it's negative 7.154 meters per second over here, that means my initial must have been the positive version of that, because it's pushing me up in the positive direction. And this one we'll go over quite a bit more in class. You may want to rewind it and play it a couple of times if you don't feel super comfortable with it yet. Number 6, Mr. Peng drops a baseball from the roof of RMHS to calculate the height of a building and notices it hits the ground 2 seconds later. The reason he used a baseball and not an iPad was to, I don't know why actually. He used a baseball though. But Mr. Peng was a teacher here a couple years ago. He ended up moving out to a different area and getting a job somewhere else. I miss him. He was a good guy. But how tall is Rolling Meadows High School? We know tall is, instead of height, we're dealing with distance in the y direction, which is the same thing as height. But that's what we're dealing with here. Well, so if I'm looking for a distance in the y, I'm automatically using my distance formula in the y direction. I can calculate the height of the building based on the amount of time that it takes this object to fall, and based on the fact that gravity's pulling it down. From here, it's a fairly straightforward problem compared to the other ones. Maybe not straightforward for you, but at least no different than the previous problems, I should say. And we come out with the distance is negative 19.6 meters, but really it's not negative 19.6 meters. It's that it fell, right, the negative 19.6 meters. So the height is 19.6 meters. Why did Mr. Peng choose to drop a baseball instead of a penny? A baseball, it's nice and round, fairly aerodynamic, and fairly massive compared to a penny, so it's really not going to be affected by air resistance. Whereas a penny doesn't have very much mass. It would constantly be flipping over and over and over again, so it would have all sorts of rotational issues going on, plus air resistance, so it wouldn't be very accurate. It would take more time to hit the ground than the baseball, and if it took more time, it would make the building seem like it was taller than it really was. All right, number 7. If Michael Jordan had this vertical leap of 1.29 meters, what's his takeoff speed? What's his hang time? Again, we're going to have to be dealing with something where he's going up and then coming back down. We know the height of the jump that he did. We also know, even though the problem doesn't tell us, the velocity at this point, again, because at the maximum height, we're always going to have a velocity of 0 meters per second. All right, so since we have a distance in the y direction, we're going to use a formula that has distance in the y direction. My initial velocity, this is my true initial velocity over here. I don't know it, but I know a velocity, so I'm going to use this as my initial velocity. We just have to realize that whatever answer I come out with is only taking into account half of this, right, including the time. All right, so I know my distance in the y direction at this point is 1.29. At that point, I also know that my velocity is 0 meters per second. I don't know my time, but it's going to be multiplied by 0 anyway, so it doesn't matter for this first part. Plus 1/2 g or a, whatever you want to think of it. Again, this is just coming from gravity, and then I'm solving for my time. All right, so go ahead, do your math. You come out with 0.26, and then we want to take the square root of that, and we get 0.51. All right, so what this 0.51 represents is the amount of time right here. How do I know it represents that? Well, because the velocity that I used was 0. Velocity of 0 is right here. What did I solve for? I solved for how much time it took to fall. How much time it took to fall is falling is represented right here. So my time for this half is 0.51 seconds. All right, it's challenging enough, but now we're throwing a big concept at this. We really have to think about where these numbers are coming from. We can't just kind of go blow through the problem just using the math alone. That's what I like about physics. Really gives you a challenge, but a good one. So it represents only half of my time. Well, that means if it took 0.51 seconds to fall, means in order to get up there, it also took 0.51 seconds. Well, together, this whole thing would be 1.02 seconds because we just add the two up. All right, to figure out his hang time, that's what we get. So if I want to know what his takeoff speed was, I deal with another equation that allows me to figure out his takeoff speed. And there's a couple ways I can do it. Assume that this is V final and be looking for V initial over here, or think that this is V initial and be looking for V final over there. We just know that whatever number we get, it has to be in the positive. So if we do it the first way around, we're going to get a negative. Just realize, get rid of the negative, put the positive value in there. So essentially take the absolute value. Number 8 is identical in terms of process. Obviously, the numbers are different. We gave you a hint down here, but we didn't give it to you before. That's kind of interesting, right? But same deal. Again, so we know that the total hang time is 6.25 seconds. So I guess it is slightly different. We're kind of working backwards here. I misspoke. But that means that if this is our total hang time is 6.25 seconds, that means this whole thing, this whole time takes 6.25 seconds. But halfway would be half of 6.25, which is 3.125. Same deal with the other half. The reason that I care about halfway is because I'm determining the height to which the ball rises before it hits, as it reaches its peak. It shouldn't say before, it should say as it reaches its peak. So when it's right here, well, its peak is halfway, so that's why I'm dealing with half my time. So then I would plug it into distance y, since that's what I'm looking for. Use my time of 3.125, not 6.25. Because again, that's how long it took me to get up there. Do my math from there. All right. Number 9 is kind of a crazy one. Same with 10. Both those are a little bit nutty, but not too bad after you hear the process. So we've got this high jumper that's going 2.2 meters to clear this bar. How long does it take her to rise up to 2.2 meters? So her maximum height is 2.2 meters right there, right? We can figure out how much time that represents, how much time it took to get to that point, again, by using our formula that relates distance in the y direction, since it's up and down that she's at currently. And we're looking for a time. Well, we know gravity is the thing that allows, gravity is the thing that determines my time in the up and down direction or in the vertical direction. So that's why I'm dealing with a formula that has distance in the y direction and gravity in it. So once I go through and solve that, I'll come out with 0.67. We've got to realize what that 0.67 represents. It represents my time from here on the ground to my time up here. And my problem is asking me how long did it take her to get up there. So that's actually my final answer. If it said something like total hang time, the total amount of time that she's in the air, then that's a whole nother beast. We can't just double it in this problem because the mat is 1 meter tall, which means she went up 2.2 meters, but she fell only 1.2 meters. Because the mat takes up one of those 2.2 meters, so she's left with just falling 1.2 meters onto the mat. All right, for B, how fast is she going when she leaves the ground? Well, in this case, we can't go with the end in mind. We're forced to use the first part. Well, I know my final velocity. It's not really my final velocity, but the final velocity that I know, at least the last velocity that I know, so to speak, is 0 meters per second. That's a really crappy m, but 0 meters per second, pretend that's an actual m. And my v initial, I don't know, that's my v naught, right? Not so sure what that is. It's a better m. I've redeemed myself. Acceleration is negative 9.8 meters per second squared, again, because gravity is going to be constantly fighting against us, whether or not it's on the way up or the way down. Gravity is constantly pulling down, down, down. And then my time, I know, it takes 0.67 seconds to get up here. So if it took 0.67 seconds to get up there, how much velocity did I leave the ground with then? Well, v final minus v initial equals at. Do my math, and I come out with 6.57 meters per second. 6.57 meters per second. All right, so with C, the mat is 1 meter off the ground. How fast will she be going when she hits the mat? it would seem like, well, if she's going up at 6.57 meters per second, isn't she going to be coming down and her final speed be at 6.57 meters per second? Well, if there was no mat, that would suck. But if there was no mat, then she would be at negative 6.57 meters per second. But there is a mat, because it stops her partway down, doesn't allow her to get down to her maximum speed, or doesn't allow her to reach her maximum speed, I should say. So we actually have to, instead of using 2.2 in the downwards direction, the only thing we got to do is do pretty much the same thing from above, except replace it with 1.2. And then we'd find out how much time it takes her to fall that 1.2 seconds. Once I know how long it took her to fall that 1.2 seconds, then I can figure out what the final velocity is using that formula. All right, number 10. We are done almost. You're on the second floor, 10 meters up of the mall. You flip a nickel 1.1 meter into the air, and it falls down to the first floor. It's like caveman speak. It fall down to the first floor in the fountain. How far did the nickel fall? Draw the picture. All right, so to begin with, you are 10 meters up. Right? If I flick the nickel 1.1 meter up, that would be up here. So 1.1 meters maybe above where I flicked it, above that above the floor. But when it falls, it's going a lot further down, right? It's not just falling 1.1 meter because it goes over the ledge, falls the 1.1 meter, which would be here, but then also the additional 10 meters that I'm up there, so making a total drop of 11.1 meters. How fast was the nickel going when it hit the water fountain? It's very similar to all those previous problems that we did. Our maximum height is not 1.1, our maximum height is 11.1, because it's falling from here and it's asking me how fast it was going when it hit the fountain. Well, it picked up speed from its maximum height, not from 1.1 meters, which would be here, but 11.1 meters. The 10 meters plus the 1.1 meters. From there, we know that it's this formula because we're dealing with a distance in the y direction, a height. We're dealing with time, and we know what gravity is. So using this formula, follow the math. Again, kind of like all the other problems that we did, we come out with t squared equals 2.27. Take the square root of both of those. We figure out that it took 1.51 seconds to fall. Well, since it took 1.51 seconds to fall, and I know what gravity is now, I can figure out what the final velocity was, because the initial velocity right here at this point is 0. All right, so hopefully that helped you quite a bit. I'm not rambling too much at 1:30 in the morning here, but rewind, fast forward, whatever you need to do, or see me in seminar to get some extra help. All right.